So for those of you who don't know me yet, I'm the current Vice President of the European Federation of Chemical Engineering, EFCE. My name is Jarka Glassey, and I'm a professor at Newcastle University in the UK. And it's an absolute pleasure to open up this webinar, one of 8 of the webinars in these last 2 weeks that EFCE working parties and sections are running in this 3rd series of webinars that we keep running. And this specific one is actually very close to my own heart on mixing. As a biochemical engineer, I know very well how we're struggling with the different rheologies and complex mixtures. So I wish I could have stayed with you, but unfortunately I'll have to apologize. And after the introduction, I'll have to drop out. Let me just say a very few words about the webinar series that, as I mentioned, we are running now for the 3rd year. We initially started running them when COVID hit, and I have to say that's the only, well, one of the very few positives that COVID brought, that it put us together in the virtual space and enabled us still to connect despite all the restrictions of physical meetings. And even though the physical meetings are now allowed, although we've just discussed that might not happen as intended in some areas still, we decided, the management of EFCE decided to keep going with the webinars and indeed start organizing 2 sets of webinars, one in the spring, which is we're running now, and another one in the autumn, because we found that they were very popular. They were bringing in a lot of audience from all the different parts of the world and connecting people that would not normally engage with some of the topics, enabling that cross-fertilization of ideas. So we're really thankful to, in this case, Working Party on Mixing, but obviously all of our working parties and sections for putting on these vibrant programs to engage the chemical engineers across the globe. If you are not familiar with EFCE, it's actually promoting and supporting scientific exchange and work of chemical engineers right across 30 different countries, bringing together something like 100,000 chemical engineers. And it is actually through the working parties and sections that the scientific work takes place. And that's the beating heart of all that we are doing. Now that we're starting the face-to-face meetings again, we hope to welcome you at some of those, but obviously we hope that you will be joining us for these webinars in the future too. I should say that the recording of this webinar will be available soon after the webinar on the official EFCE YouTube channel. So please look out for it if you don't manage to stay for the whole of the webinar like myself. And you will also find some of the other webinars from the past are available on there. And I don't want to hold any more of the floor or the screen, but I still wanted to thank everybody for putting all the hard work into organizing these webinars. And that greatest thanks really goes to Martin too, from Toulouse, who is basically organizing them for 3 years now, and she still didn't get sick of them. So thank you very much. Thank you very much, Martin. It's very much appreciated, but obviously to all the speakers as well, and all the working party committee for pulling all these presentations together. And with that, I'll hand over to Joelle Aubin from Working Party on Mixing, who is, I believe, the current chair. Yeah. And I'll let you then to just take over the running and tell the audience a little bit more about the organization of this webinar, and just wish you a very successful webinar this afternoon. Thank you.
Thanks, Jarka. So welcome everybody. Welcome to this 3rd edition of the Spotlight Talk series. So the Working Party of Mixing has organised one every time, so we're really pleased to be back again. So as Jarka mentioned, I am the current chair of the European Working Party on Mixing, and I'm accompanied today by Claudio Fonte, who is also the secretary of the Working Party. Now, I'm a senior researcher in chemical engineering at the University of Toulouse. So today our topic is on how do we overcome the challenges of mixing processes that have evolving rheology? So processes that have evolving rheology are encountered in all types of industries, ranging from foods to personal care, pharmaceuticals, paints, lubricants, polymers. And this change in rheology or viscosity occurs sometimes for some physical reason, due to some type of microstructuration of the flow of the medium, or from chemical reaction. What it does involve also is many challenges, principally related to the change of flow regime. So we might go from turbulent flow to laminar flow, transitioning through the transitional flow regime, or vice versa. And this means that mixing can become difficult because maybe our mixing system might be well designed in one flow regime and not so well designed in the other. So how do we do it? And what are the underlying physics of the flows? Okay, how do these flows change and evolve during the process? So this is the challenge that we've put forth today, and we have invited 4 speakers. I'm just briefly going to introduce each of them, and then you'll get a chance to listen to them, of course. So we first have Professor Mark Simmons from the University of Birmingham, who's going to give us a general talk on mixing challenges in these types of processes. Then we're going to be listening to Dr. Tom Rodgers from the University of Manchester, and he's going to be talking to us about experimental measurements of these systems. Then we go to the University of Aberdeen, and we have Professor Derksen, who's going to talk to us about simulating complex flows like this. And then we go across to the other side of the world, and we have our Dave Dickey, who's a mixing consultant for Mixtech, and he's going to go towards more practical applications and teach us or inform us, tell us best ways to design, scale up, and approach these mixing systems. Now, just a couple of practical bits of information. So as participants of this webinar, you do not have access to speak, okay? If you would like to ask questions to any of the speakers, I invite you to ask them by writing the questions in the question and answer tab that you'll see on the screen, okay? Please use the question and answer tab rather than the chat. Then Claudio, at the end of each talk, he will read out each of your questions to the speaker, and the speaker will answer them. If we go over time, then the speaker will answer the questions for you by writing a written reply, okay? I think that's all I have to say. So now I'm excited to listen to all these different talks. So I'm going to pass the floor over to Professor Mark Simmons. So he's going to talk to us about mixing challenges in the formulation of complex microstructured products.
Okay, thank you very much, Joelle. I hope everybody can see my screen okay. If I can get a few thumbs up, that'd be really handy. Yeah, that's great. Okay, so Joelle's already kindly introduced me. I'm here today to talk about mixing challenges in the formulation of complex microstructured products. And Joelle's already actually done a great job of introducing the particular topic. But if you'll excuse the rather UK-centric title here, formulated liquid products are worth about 180 billion to the UK economy. I mean, it's home and personal care, foods, pharmaceuticals, it's a really big area. But the processing of these materials is very complex. You're starting off perhaps with an aqueous-based rheology, you're adding materials into it, that's causing an increase in viscosity, which may ultimately cause, of course, a change in flow regime. These materials have got complex rheology, complex microstructure, and they're typically multi-phase. So they're hard to process, and we need to find ways as engineers of being able to do that, particularly as we change formulation, changing to new ingredients, Perhaps we're changing to greener ingredients that might inherently be more variable in their properties. How can we make sure that we maintain that product quality? And of course, very importantly, if it goes wrong, can we get it back? Because if we mix badly and we get the wrong microstructure and there's nothing we can do about it, we've got a big sustainability issue with lots of waste. So I hope I'm not going to flit around too much today, but I thought it would be useful to give a bit of an impression of 3 current areas of work that we're doing in our labs in Birmingham, together with our partners, including Joelle actually, and David Fletcher at the University of Sydney. The first thing I'm going to talk about is mixing and transitional flows, because that's clearly a really important area. How do we actually go about simulating the flows when we're in this very difficult and poorly understood regime? So that's more of a sort of a processing end. Then the following 2 case studies are more about looking at the product and the product quality as a function of the processing conditions. And I'd like to start off by talking about microstructural development in the processing of an FMCG product, in this case, hair conditioner. And then finally, probably the most complicated but least understood is the formulation and mixing of battery electrode slurries. So I'd like to start off by talking about mixing and transitional flows. And this is some work that we're doing in partnership with Unilever and with Joelle and David Fletcher. And it's really building on trying to understand how we can develop or how we can use closure modules in CFD that will give us a good, reliable answer when we're moving into the transitional regime, either because we're moving from turbulent down into the transitional regime, or possibly moving from laminar upwards. So we've started some work following on from a study by Mendoza et al. In Joelle's lab, looking at how we might simulate a stirred tank reactor, in this case equipped with an A320 hydrofoil at various Reynolds numbers in the transitional regime. And what we really want to do is assess the suitability of those closure models and what we might do to modify them to make them work if they don't. Now, the work started off by looking at a stirred tank, and we did have some initial early success with that. We're using ANSYS fluent simulation. We're using what we call a dynamic stress blended energy simulation model, which is a recent type of model that uses a K-omega model close to the wall and then moves to switch into an LES model for computational efficiency away from the wall. And our initial results were quite promising, quite encouraging. We were able to achieve mesh independent results with good quality. But what we started to realize quite quickly was that when you're trying to compare the results you're getting from the CFD with experimental work, it becomes very complex because you've got a change in the flow regime happening. We know it's extremely sensitive to any unwanted perturbations in any experimental setup. So what we decided to do was to take a bit of a step back from that and actually do some experiments on pipe flows. So what we thought we would do is we would have a pipe flow in the transitional regime and use a square-edged orifice plate to create a disturbance, and then see how those disturbances propagated as a function of Reynolds number, comparing the CFD with the PIV at each case. What we've done is we've used SBES model, again, predominantly in the fluent simulations that we carried out. So you can see the geometry here. So there's the pipe there. You can see the diameter of the pipe. You can see the orifice plates, and you can see the mesh that we created. And we're basically doing the PIV, looking at an axial distribution of the flow. So just to start with the CFD model, if you're using SBES, you do need to do some initial checks. So the first one is to make sure that the Coron number, of course, is about 1 or less. We also need to make sure that the Y plus values are okay and within a range to ensure that the K-omega model is able to integrate down to the wall and that the LES doesn't switch in and produce some sort of wall function close to the wall. And we can also check that by looking at something called the shielding function, which basically indicates the region in which the model switches between K-omega, which is the red near the wall, and LES in the bulk. And we were basically able to demonstrate, I think, that the simulations were behaving as one would expect. So the first thing we actually did was to check the Reynolds number independence of the model. So for our two experimental fluids that we used, we simulated these are two glycerol water solutions of different concentration. And what we can see is if we look at the normalized velocity magnitude is that we've got a pretty good agreement in flow in this sort of recovery and flow development length downstream of the orifice, both at the same Reynolds number of 2030 for these two different fluids. Of course, as one might expect for the laminar flow model, we see a much longer flow development length. We also had a look at the turbulent properties. I mean, for a laminar model, it's a moot point what that actually means. But of course, for the SBES model, again, we're seeing a reasonably good scaling with the Reynolds number and a good behavior, well-behaved solution. But the question then is what actually happens when we start to compare this with the particle image monosymmetry results. So these are the initial results from our PIV simulations. So what we're seeing here is the normalized time averaged axial velocity down the center line of the pipe as a normalized distance downstream from the orifice plate. So what you can see is that how that velocity changes as a function of the Reynolds number of the flow. And quite encouragingly in the turbulent regime, we're seeing that the flow development length becomes independent of viscosity as one would expect. But then what we see as we move through towards the laminar regime, we're getting a longer flow development length with some behavior in the transitional regime, which does seem to behave well as a function of the Reynolds number. If we actually look then, so that was really just to make sure that a sanity check on our PIV data. What we then did was to look at how the velocity profiles were changing downstream of the orifice plate for the two different solutions. So the PIV data are the dots. And you can see the three different CFD models indicated by the lines. And you can see that generally what we tend to find is that close to the orifice plate, we're getting pretty good prediction. As we start to move further downstream, the SBES seems to give by far the best prediction, but we do see some discrepancies as we move from close to far away. Now, one thing we've started to realize is that it might well be that there's some differences in the initial disturbances caused upstream of the orifice plate, which are starting to affect how our flow is behaving. So the next set of work we're going to do is going to be to look at how we might address that in terms of doing measurements upstream of the orifice and looking at the disturbances as well. But nevertheless, for a high transitional flow, we seem to be getting some results which are not incompatible between the CFD and the PIV. So yeah, so that's just some very, some early interesting results there around transitional flows. We've chosen a pipe flow to better understand the mechanics of play. The SBES shows the potential to represent features of high transitional flows, but we need to think more carefully about how the upstream disturbances might be affecting things. And we are getting a reasonably good scaling of the Navier-Stokes equations with the Reynolds number using the SBES models. So the next steps are to look at the upstream disturbances and finally, of course, once we've done all that, we want to take the learnings from the pipe flow study into the modeling of the transitional flows in the stirred tank reactor. Okay, so that's the first one. The second one is following the microstructural development in the processing of an FMCG product. This is the hair conditioner. So hair conditioner, as those of you who've got hair, mine's falling out. But anyway, the idea behind the hair gel product is the hair conditioner product is it's a lamellar gel network. So it's a mixed crystal bilayer of fatty alcohol and surfactant. And basically, it's got layers, and then you've got interlamellar water in between them, which gives it specific properties. But formation of the right lamellar gel network is quite complicated, and getting it right is critical, because the problem is that if you over-process this material, you can actually get it to the point where you can't bring it back, and then you've got to waste. So this is something where you've actually got to process it well and get it spot on straight away. So this is the structure, and this is the mixing operation that makes that structure. So you have a very complicated industrial mixer. You have a sequential addition of raw materials. Of course, as you add these in, the fill level is changing. As you add in the different ingredients, the rheology is changing massively, as is indeed the mixing efficiency. And of course, you've got to get the right product quality, and you want to make sure that you do all of this in the minimum time with the minimum power. So, you know, kind of no pressure here, it's quite complicated. But in issue, the main issue here is that how we actually mix the materials together. You've got an oil phase and an aqueous phase. You homogenize, you add surfactant, you cool, and you add your final ingredients. So what we wanted to try and do is to see, is there a way we can actually simplify this very complex mixing operation into one that we can start to understand the interactions of the individual components and get some idea of the kinetics, if you like, of the formation of this lamellar gel network. So what we actually did was we decided to use a rheometer, if you like, as the mixing vessel. So this is a rheometer equipped with a vane geometry, and of course with a rheometer you get very highly accurate measurements of torque as a function of speed. And we wanted to see how, as the viscosity developed, the amount of power we're putting into the material was changing, and how the actual viscosity of the material was changing as a function of time, temperature, and agitator speed. And all the idea here is to understand the relationship between power and energy and the viscosity of the material. So this is what you actually see if you carry out this particular operation. So what's actually happening? So you mix the water and fatty alcohol at 70 degrees C, and that's a relatively low apparent viscosity. Then you add in the surfactant then melts and the structure starts to build. And it builds to a peak, then it goes to a steady state, and then you cool, and then you have your final product. So the question was, how does the shape of this curve change as we go about processing the material, in this case in the vane rheometer? So the first thing we did was vary the agitator speed, which obviously gives a different characteristic shear rate in the vane rheometer. And what we found was that as we increased the shear rate, we got the peak viscosity occurring sooner, but obviously the power requirement is increasing quite considerably as a function of the increased shear rate. But these are the yield stresses that you can see generally tend to increase a little bit as a function of the increasing speed. So the yield stress, if you like, is the quality measure we're considering in this case. If we change the time over which we do the mix, then the steady state viscosity was achieved after about 15 minutes, but the processing time can be reduced and you get the higher product quality. So again, you've got this trade-off obviously between power and time, but you can also maintain the quality if you're changing the overall time of the mix. So what, I mean, obviously I could produce quite a few of these different graphs showing these different parameters and how they change as a function of each parameter. But I think what's really interesting here is when we actually started looking at how the power per unit volume that we actually have to achieve the peak viscosity. And what we actually found, or perhaps I should say energy per unit volume, here it's in joules, okay, was that the energy per unit volume or per unit mass required to achieve the peak viscosity was always the same. So if you integrate under the graph to the peak, we always got the same value. So this becomes useful because it starts to tell us something a little bit about how the processing is working. So if we can optimize our stirring speeds to ensure that we get the right energy into the material at the right time, we should be able to therefore optimize, perhaps on a larger scale, the batching time and the batching shear rate that we're actually targeting. So that's as far as we've got so far with that. I mean, clearly what we've done is something on a very small rheometer, and I won't pretend for a minute that it's going to behave exactly the same as a larger scale mixer. So the next step is to start to do that, is to start to test the principles we've developed, the relationships between energy and power on larger scale mixers with industrially relevant geometries. And then we can move also to looking at that and the characteristic microstructures that are being developed. Okay, so the final thing I'd like to talk about today now is the formulation of lithium-ion battery electrode slurries. So this is actually quite a poorly understood material in a mixing sense. And obviously it's a very important one given the needs for more and more lithium-ion batteries. We need to make more batteries and we need to make them better. And as we know, for the number of gigafactories that are being built around the world now. So these slurries are quite complicated because they consist of an active material. In the case of the cathode, it's a mixed nickel, manganese, cobalt, lithium oxide. In the case of the anode, it's a graphite material, and they form the majority of the slurry. So it's a really high solids fraction. Included in there, you've also got a binder, which are generally polymer binders, different ones in the case of whether it's the cathode or the anode. So that's PVDF, that's carboxymethyl cellulose, and that's styrene butyl rubber. And then what you also add in is a conductive additive, and this is a nanoparticulate material, generally a carbon black of a different grade between the anode and the cathode. But those are nanoparticulate, whereas the other particulate materials are more micron size. So you've got a pretty complicated matrix there comprising the polymer, larger particles and smaller particles, and how they arrange themselves in the microstructure is really important to the performance of the battery. And perhaps unsurprisingly, they are shear thinning materials. So what have we been doing? Well, we've been looking at how we might scale up the mixing, and that becomes problematic because what you actually need to do is need to be able to make material at different scales for testing, but also for production. And what's used quite a lot by the batteries industry is quite bespoke designs of mixer. So the one at the top here, which is probably my least favorite mixer I've ever seen, is what they call the Thinky mixer, which is like a planetary mixer where you have a rotating pot, which is then rotating about a larger axis. It's a bit like a glorified centrifuge, if you like, and which is like 50 to 100 milliliters. So it's very popular because it produces small amounts of samples for testing. And then as we move to the lab or pilot scale, you've got this IRIC type mixers, which can go up to actually 50 liters or even 500 liters in size. And that's equipped with a rotating pot, a scraper, and some sort of turbine in the middle. Now, what happens if you get the mixing wrong? Well, the answer to that is it's pretty catastrophic. You can see here, this is a graphite slurry, so this is the anode slurry. And you can see if you don't wet it out properly, you get effectively a mechanical gel that you can't process. And there's two things that can go wrong. If you don't wet out the graphite, then all these graphite particles, which are the big blue ones, will actually stick together in chains and form a mechanical gel, and then you can't wet it, you haven't wetted it out, it won't coat. The other thing that can happen is that the conductive material can end up on the active particles rather than being incorporated into the polymer chains. And the idea is you want it incorporated into the polymer chains to provide a good conductive matrix for the battery electrode. So there's quite a few mixing challenges in here in terms of getting the final product right. And one imagine, as you might, well, I don't think I need to say this, do I? But clearly moving between the different mixers and different mixer types is quite a challenge to make that scale. So we've done a couple of things. The first thing that we've done is to look at the flow within these mixers. So we've used positron emission particle tracking, which is a technique which is available in Birmingham and also in South Africa. And it's a nice technique because you can add a radioactive tracer to the actual mixer, which is a positron emitter, and you can locate the position of the tracer using detectors from positron cameras, PET scanners, positron emission tomography scanners, and you can detect it in opaque materials, in metal equipment. With the older technique, typically at a meter per second, you're within a half a millimeter at 250 hertz. The new Super PET, which we've just recently commissioned, gives an order of magnitude improvement in both of those. But what we were really interested in doing is trying to track how these materials are actually mixing within the vessel. So this is the Thinky mixer, which is the work done by Sam as part of the Nextro project. We include the mixture in there. We put one particle on the pot so we could see the location of the pot as it rotated around its dual axis, and also one particle in the actual fluid itself. And from the position of the back-to-back gamma rays positioned by the produced by the particle, you can triangulate its position. And so what we can actually see on the right-hand side is the position of the pot as it precessed around inside the mixer. And you can see that there's actually some drift. It should all be one line, but it's actually drifting due to the fact that there wasn't quite accurate enough speed control on the mixer. But nevertheless, we were able to detect the position of the pot, and we were able to detect the position of the particle moving around inside the pot, which is the red trace here. So it's quite useful because what we want to be able to do is really to assess the regions where this thinky mixer behaves well and the regions where this thinky mixer behaves badly. Quite often, practitioners are using standard operating procedures and they mix it for a certain time at a certain speed and think it's all done. And our data is starting to illustrate that that certainly isn't the case. We're still working on it. I mean, this is a work in progress, but nevertheless, the fact that we were actually able to, for the first time, to look inside this mixer and see what it does should enable us to help practitioners. The IRIC mixer is a little bit less complicated because at least if the bowl is stationary, even if it is rotating, it's not orbiting. But we can see how the mixing pattern changes as a consequence of the changing bowl speed. So this is initially just done with the binder in water. And you can see that as we increase the bowl speed, the fluid starts to wash up the side of the bowl. As we add the graphite in, as one might expect, we start to see the viscosity change and see a dramatic difference in the behavior of the tracer, not only in terms of its speed, but it looks like the energy is actually being transferred a little bit better to the fluid once it starts to become more viscous. It's probably because the fluid is starting to move down more towards the bottom of the vessel again as we add in the graphite. But also, the next question will be to see how we can calculate mixing indices from this data as a function of the recipe and as a function of the addition. Other work we've been using electrical resistance tomography and other to actually look at overall macro to mesoscale mixing. We found we've been able to track quite nicely the behavior of the graphite as has been added into the mixer. You can see the big lump on the side that hasn't mixed in there. That's been picked up really quite nicely actually by the ERT. But less crudely, we can split the tomograph into a series of zones. And we can see that when the graphite was added into zone 8, we can see how that then became incorporated, or the lump then moved into a subsequent zone, zone 7, and then see how it's actually then brought back to a sort of more homogeneous condition over time. So we can get some sort of rough idea of an overall macro scale mixing time as we're adding each of the components into the slurry. We can also be a little bit more subtle by taking offline electrical impedance spectroscopy measurements. What we're able to do is to actually detect from a frequency spectrum the distribution of the carbon black as a function of the mixing time. So as we distribute the carbon black better, we should end up with a more conductive matrix. And that's something we can actually pick up from the spectroscopy. There's what we call the knee frequency here, which you can see has changed as a function of the mixing time. And generally, as the lower knee frequency leads is effectively saying it's a more conductive matrix. So this is quite a nice subtle way that we've only recently discovered, maybe picking up some properties of the mixing from perhaps a more sophisticated method that's generally used by battery people. Okay, final slide, because I realize I'm running out of time here. But we have been using rheology as a mechanism to try and understand our microstructure as well. So on here we have two identical slurries mixed on two different mixers, the thinky and the IRIC. And you can see that the IRIC has produced a slurry from its standard operating procedure that's about an order of magnitude higher in viscosity than the thinky. And the question is why that might be. Well, we know that if we mix it badly, then we get this kind of mechanical gel being formed, which has got quite a high apparent viscosity. But we also know that if we start breaking down the agglomerates of carbon black in the mixture, we also start to raise the viscosity. So increased viscosity doesn't necessarily say the slurry is good or the slurry is bad, unless we use it in conjunction with something else. And the other thing we use here is some oscillatory rheology. And what we tend to find is that if we've got good distribution of the graphite and we're improving the distribution of the carbon black, what we generally tend to see is that the G double prime, the viscous modulus is above the storage modulus. So we've got some degree of viscoelastic behavior, but it's still flowing. So using rheology in tandem with the EIS or the ERT, we are starting to get an idea of how we can understand the microstructure and the microstructural development as these slurries are manufactured in the mixers. Okay, so last slide from me on the technical. So scale up and down of battery materials is obviously complicated by microstructure requirements and different mixer designs. I think the key to all of this actually is you need to use a lot of different methods in tandem to really understand what's going on. You can't just rely on one method to really understand how your microstructure is changing. You know, if you're just measuring rheology and you think, well, the viscosity is the measure, well, clearly in this case, it's not. You need something else as well, because lots of different microstructures might be giving you the same viscosity. You need to be more subtle. And I think our future work is going to be to assess a wider range of formulation and mixer types and scales. And ultimately where we want to get to is to develop practical guidelines for practitioners and scale up, including mixing indices. So I'll just finish now by saying thanks to all the collaborators, the people without whom this would have happened, to, of course, all our sponsors as well. Thank you for listening, and any questions? So I will.
Thanks very much, Mark.
Thanks, Mark. I have a couple of questions online.
Okay.
So I have a question from, I'm assuming it's Ravindra Aklave, because it was posted at the same time in the chat and in the Q&A tab. So I think it was around your slide 17. He's asking what constitutive equations were used.
Okay, slide 17. Okay, this is for the let's just have a quick look. This is for the sorry, I'm getting there. This is for the lamellar gel network, is it? Oh, okay. So the apparent viscosity is taken by just from the measurement of the shear stress and the shear rate from the vane rheometer. We've not assumed any constitutive law at this point. Yeah, is that right?
So, maybe if that didn't address the question, maybe the person who asked the question can type a little bit more.
I'm assuming that's what was asked. But
and I have another question as well from Alain Linet. Hi, Alain. So he says, thanks, Mark. Nice work. In transitional flows between laminar and turbulent regimes in pipes, are intermittent structures observed in experiments and in simulations?
Okay, I think that's a really interesting question. I mean, obviously, what I've shown at the moment is just the average velocities and things. I mean, we are observing some periodic structures being formed as the flow comes through the orifice. You do see some deviation, and certainly that's something we do need to look at in more depth. But we haven't as yet looked at that in depth, but it's certainly on the to-do list. Thank you.
Maybe I can ask a question while people type their questions online. So in your rheometer as a mixer, so what you were saying is that what it matters is the amount of time or the amount of energy that you are putting per amount of material inside, and not really how fast mixing is.
Yeah, I mean, this is it. So certainly within the range of parameters that we use on the rheometer, where we're trying to input, if you like, ranges of power per unit mass that would not be incompatible with what you might do on a process larger scale mixer. It seems that to get to this peak viscosity, it's the total energy per unit mass that matters, not the power per unit mass. So obviously, if you run at a higher power, you'll get there faster, but you're running at a higher, but your energy cost is higher. Whereas if you run it lower for longer, yeah. So the question is, we should be able to find an optimum, in that space. Yeah.
And have you tried to operate it in a kind of an oscillatory mode to get other types of rheological measurements while you are mixing the material?
We have done that, and in fact Unilever do that as a matter of course, because they, these materials are obviously, they do have strong viscoelastic type behaviors in certain flow regimes. But what we were interested in doing with this particular piece of work was trying to say, if I've got a mixer and I can measure the torque on it, regardless of scale, and I know that gets much more difficult as you go to larger scales, but the point should be that if we can understand what the power we're putting into the material, then we should be able to understand where our endpoint ultimately is.
I have one more question from Archie. I'm sorry if I'm butchering the name, Nico Sam. Are particular modes of operation of the Erich and Thinky mixers empirically associated with good or bad products?
Yeah, absolutely. And the challenge has really been that quite a lot of the standard operating procedures that have been developed for these types of mixers are highly experiential. So you've had a formulation that has been decided as the gold standard, and you basically run with that formulation for a long time. You then change your formulation, or your supplier of a particular material changes, or the batch changes, and then all of a sudden, your material that worked absolutely perfectly yesterday doesn't mix on your mixer anymore, and you don't understand why. And it comes back to small batch to batch changes in material, and can cause quite large changes in the microstructure for the same operating procedures. So yeah, absolutely. And so this is why we're trying to do this work, to try and see what is the inherent variability in all of the materials and in how they might affect the mixing of these battery materials. I hope that answers the question.
Okay. Great, thanks Mark for all these answers. I think we're going to move on now.
Okay, thank you.
Great talk, very interesting.
Thank you.
So the next speaker is Dr. Tom Rodgers from the University of Manchester, and he's going to give a talk on measuring mixing in viscous and evolving rheology fluids. Over to you.
Okay, thanks, Joelle. Hopefully you can all see what I've just popped up on screen. Excellent, thank you very much. Yeah, so I suppose it follows on quite well from Mark's talk in terms of examining specifically in this case sort of mixing times when we've got these sort of very difficult to handle fluids, whether it's just due to high viscosity or whether it's due to essentially we might start in one regime, move to another, or at least sort of big changes in rheology, and trying to understand what we're actually doing when we do that. So obviously I didn't do all this by myself, so I'll leave this slide up for a few minutes, a few seconds while I go through sort of a bit of an outline. So we'll look at essentially mixing some systems where, although the rheology doesn't particularly change of our main fluid, we're actually adding something of a very different rheology. Then moving to sort of high rheologies, and then how the addition of material changing rheologies, we can look at and examine that. And then actually, interestingly, we'll revisit the wonderful material of hair conditioner that Mark described as a material very well for us, so I won't need to do that, which is great. Which in this case is very interesting because the rheology of the hair conditioner actually evolves just through the mixing in the state that we're examining it here. So we're not actually adding any material. It's the it's purely the shear that is applied, or the energy that is applied, that actually changes that rheology. So how can we think about that? So this sort of starts by looking at adding something, much different viscosity to one viscosity. So in this case, we've got water. And what we're actually doing is adding a surfactant to this, so a very high viscosity material, and it dissolves or mixes within the water. So in this case, it's sort of a standard operating procedure. You just get a bucket of it and drop it in. You can see it falling in there. And you've got all kinds of horrible things happening. In this case, there's some stuck on the back of our tank. You can see large pieces moving around, breaking on the agitator. How do we actually sort of monitor that process? Okay, so through this talk, I'm essentially going to be thinking about how we're going to do that with one technique. So if we've got, say, a person, or in this case, a rabbit, and we want to look inside of that, I don't think anyone would be surprised if we say, oh, well, we can sort of x-ray it and we'll get a nice view inside. Okay? But of course, we can't really do that if we're in the lab, or we're actually in our plant, as we've got x-rays flying around, or we've got metal lined vessels, etc. So we can move to a technique that sort of gives us a similar idea of being able to look inside our process. So I'm going to be focused really on electrical resistance tomography today, which essentially is where we're applying a particular current across electrodes on our vessel, and then we're measuring the voltage response at different positions on our vessel, and that allows us to get some kind of map of the electric field all within our vessel. So the advantages for us is that it's a lot safer than, say, x-rays. It's a lot faster than x-rays. It is possible to get 1,000 frames a second, so we can image very fast flows, or if you've got a slower process, you can take multiple images and sort of average them to get better data. And we do this, and we can have lots of different layers in our system to measure it. So if we go back to our nice mixing system here, you can actually see that the vessel we used has these rows of electrodes along the outside of the tank that we're actually using to do our mixing. So I won't spend loads of time going through any maths, but essentially there's two steps to the processing. So we generate what's called a sort of a forward problem, which gives us the idea of the sensitivity map that we can get within our vessel. And it tells us where we're monitoring, and it allows us to then reconstruct what we can see from those outside measurements. And then taking that, we can essentially create an inverse problem, which allows us to then actually get that image. So you can see two examples here where we've got sort of phantoms put into our system, and we're reconstructing the shape and the location of these. And in this case, we've added a large amount of noise to kind of replicate, the tank all moving around and an agitator spinning, as I'm sure many people are familiar with when you sort of turn these things on. So then coming back to the video we looked at, so what type of information do we get out of the system? Well, in this case, we can actually, because we've got such a large piece of material falling in initially, we can actually resolve that large lump coming into our system. So in this case, we've got our lump falling into our system, our low conductivity sort of continuous water phase, and our high conductivity sort of surfactant being added as a lump, we've got interaction with the agitator, we've got splitting of the lump into two pieces. After a certain time, as you could sort of see in the video as well, the lump was sort of broken up and it forms these little thin strands. And we can't detect each individual strand using the tomography technique, but what we can do is see them dissolving, because we get we can see the conductivity of them. So as they slowly dissolve until we get a dissolved homogeneous system at the end with our surfactant dissolved in our water. Interestingly, I've actually put this red line in here, and this red line is the point where you can visibly no longer see any of the strands. So when this process was originally designed and people were essentially watching it to the point where it looked like it was mixed because there was no surfactant strands left, they weren't actually getting the end of the operation condition. It was actually still dissolving with strands, but they were just too small to be visually seen. Okay, so and this system was quite interesting. I think shows some of the challenges, especially around this, where we can actually measure a mixing time for these systems. But really interestingly, and I think one of the great challenges is that actually we get two trends depending on how we actually add the material to the tank. So if we do what's titled here as an injection, the more sort of orangey line, the bottom line, then we get sort of a strand, and that strand quite easily breaks up within a system and mixes a lot faster than if we do what's attributed here as what's called a lump, or the lump addition method of the green points, or this top line, where essentially we do a more standard approach on a large scale system, which is you have the material in a bucket and you tip it in the top of the vessel. So actually when we're dealing with these sort of different rheology systems or different viscosities of our adding material and the base material, the method that we're adding them really affects how we're actually the overall mixing time that we actually get. So let's move on and think about some mixing with Newtonian fluid. So we're changing the viscosity of our fluid, but actually whatever shear rate we're under, that fluid has the same viscosity. So this is quite a small sort of lab scale system. You can see it's just over a litre. We've got our tank here. We've got our electrodes on the side of our tank, so we can apply the tomography technique. And then we've got this sort of angled six blade pitch blade turbine stuck into our tank. Okay, so this, as we can imagine, is a relatively poor mixing system generally, but especially when we get to any type of high rheology, we're probably not going to be mixing that well in our system. But with our ERT, we can essentially look at analysing this. So we're using different concentrations of glucose. So we're changing from a water-like viscosity up to about 1,500 times the viscosity of water. And we're adding essentially a small trace of material the same viscosity as what's actually in our vessel. And we're using or taking advantage of the fact that with the ERT method, because we get this distribution across the whole vessel, we can say divide our vessel up into zones, or we can get sort of an overall measure. But in this case, we're going to be dividing it up into zones to allow us to see what that actually or how the mixing actually takes place within our vessel. So in this case, within each zone, we're sort of applying a local measure of our T95 mixing. So we're saying when a particular zone is classed as mixed, with then essentially no more changes it really within that zone. And you could see that when we've got a more high viscosity liquid, so this is a Reynolds number of 22. So high viscosity fluids, we've actually got a large distribution of when sort of the mixing can be considered finished within our vessel. So, you know, if we were potentially measuring in this top cell over here with say a point probe for our mixing, or we were looking at this sampling from this area to think about the mixing, it would be a completely different story than if we were sampling in this red area, which takes over about 5 times the amount of time to actually get to a homogeneous value. Okay, so that shows us another big challenge when we're moving to sort of our viscous mixing, that, you know, what are we actually considering to be a mixed value. So in this case, what we're doing is we're looking at the sort of endpoint for the whole vessel based on these. So we would consider this 22 one here to be more 125 seconds for when we can consider the total contents to be mixed. And if we do that for these different systems, we get this sort of fairly standard sort of mixing time versus Reynolds number and power number here system. And we're sort of getting the trends that we expect, but we are measuring that end mixing time. So, I mean, nothing too, I suppose, surprising for viscous systems, but it is showing us that we've got this real inhomogeneity of mixing times within our vessel. So let's move on to a system that's probably slightly more useful in the more viscous areas. So this is exactly the same experiment. So I'm going to go through it, but with an anchor mixer in there. So we produce exactly the same type of trends, but of course different values to with our pitch blade turbine. So if we're now going to think about adding a different component, so in this case, we've just got some shear thinning material, so some different concentrations of xanthan gum. So what are we actually using to replicate the viscosity? So there's no evolving rheology necessarily by adding anything, but it's a shear thinning material, so the anchor moving all the different shear rates within the vessel does that. So actually we get relatively good approximations by just taking an average approximate shear rate from the anchor spinning from a Metzner-Otter style relation, and that allows us to map that the mixing time quite well onto our same lines here as our Newtonian one. So this dotted line and this straight line are unchanged from the Newtonian data. Okay, so that's nice. That tells us we've got some potential confidence that we can do an approximate shear rate and a modified Reynolds number based on that viscosity to actually still approximate our mixing time. So what if we then take another step of interest and we look at something like shampoo? So if we've got a shampoo, adding salt to our shampoo actually changes the rheology of our material. So say we were going to add a salt tracer to our shampoo, or add salt actually within the manufacturing of shampoo, which is a typical step, we actually get a material that has a rheology that changes based on that concentration of salt. So as the salt concentration is moving around the vessel, we can have evolving rheology in the vessel. And if we take a single representative point on our rheology diagrams at different shear rates, so if we take a representative point at the same shear rate, then we get these type of curves here. So we get a addition or an increasing viscosity as we partly increase the salt concentration, but then we get to a plateau, and as we drop down this plateau, you know, as we add more salt, we start getting a reduction in the viscosity again, and this is due to essentially how the salt is interacting with the microstructure within our shampoo. And the horrible thing, I suppose, for us in terms of mixing is that when we start to fall over the plateau, although the viscosity or average measured viscosity actually decreases, the material becomes increasingly more and more viscoelastic. So we get much more time dependent issues occurring rather than just a viscosity we can think of as more of a steady state system. So we can look at sort of adding different salt concentrations. So we're adding different amounts. So if we repeated this activity but with a Newtonian material, as we added more and more concentrations of salt to this, or in number of addition steps, we would expect that mixing time to basically stay the same, because adding the salt isn't necessarily affecting the rheology. But in this case, not only do we get the mixing time changing with our continuous number of additions, but it changes differently depending on the amount that we're adding, which I suppose when we think about the rheology is not that surprising. So how do we, or how can we kind of put this together to give some indication of how long it takes to mix? So it seems to turn out that, at least with the shampoo system, that if we look at the viscosity of the end point, so our end point condition at the end of that individual addition, that is the one that seems to help us to actually bring mixing time information back to what we would expect as our base case condition, which we can think of as the Newtonian case. Okay, and I suppose I should draw point to these sort of 4 points here, which are not really fitting any that close to our line, and these are actually the highest concentrations of salt at the end point, and these are ones that have actually fallen over the top of our curve. So we're seeing additional sort of viscoelastic properties, and also technically the viscosity as we add that salt is actually reducing into our system. So this is probably a different sort of metric that we're not taking into account by just sort of looking at that end viscosity, and also thinking about an average shear rate within our tank representing that viscosity. So as sort of mentioned, Mark originally gave a very good introduction to hair conditioner. So not only is it sort of shear thinning under different shear rates, but the shear actually changes or can change the rheology of our final product, and consequently the conductivity. So if we've actually got our tank here, so we've got a tank of sort of our made shampoo, it's then quite common to actually do what's called a post-shearing process, which is to send this material around through a high shear mixer, in this particular case a Silverstone mixer, and then bring that back into our vessel to actually post-shear, which changes the viscosity of the system. And essentially what that shear is doing is adding energy to our system, which is rearranging that sort of very complex microstructure that Mark introduced to us, and then that's being reflected as a different viscosity within our system. So we can monitor that process actually with our tomography technique. So this first sort of image here is our hair conditioner that has not been post-sheared, and it's still very viscous, but it's a bit sort of dull, I suppose. If we want to go into personal care terminology, it's sort of dull and lifeless, and doesn't look very appealing to the consumer. And after our post-shearing process, you can see not only is it more viscous here, but it looks more like the hair conditioner we're familiar to seeing in our bottles. But what we're actually seeing here is we're actually tracking that change in conductivity, which is a mirror of that change in viscosity, actually as it's going through our post-shearing process. And we're taking it out at the bottom corner, and we're putting it in at the top corner. So you can see not only is it taking a long time to mix through our vessel because of the high viscosity, but we've got a change in rheology just due to that post shear. And the interesting thing is, it's just the shear. We're not adding any other material, so it's not like we're adding something more conducting to this. And then these are great because we can actually then use this to track it, and you can say we can use it to track around when our process is finished, and you can see, depending on different shear rates, depending on different flow rates through, we get different levels of this conductivity and sort of different viscosities measured from that. So we can track a whole variety of how that material is changing. So really, I've shown, I suppose, a couple of successful examples around sort of either evolving rheology or looking at how we might measure these more complex rheologies and mixing time for them. And it's all this has sort of been based around ERT, which means that we've needed to have some kind of variation in conductivity. And to understand what that is actually referring to in our system, we need to understand what does that conductivity relate to. So is it purely a change in conductivity due to just, say, adding something more conductive, or are we getting a change in conductivity related to a particular microstructure change within our fluid? And this is where we can couple with other techniques to give us extra information. And of course, we also need a good model for actual reconstructing if we're looking for those images of our system, and that's a mathematical solution to that. But if we do have systems where we can do this and we can understand this, it does seem like we can actually at least monitor these complex rheological mixing systems to actually get, say, mixing times or understand local concentrations or microstructure from that. At that point, I hand over if there's any questions. I think there's still a few minutes in the allocated time left.
Thanks, Tom. There are a couple of questions. A question from Alain Linet. In experiments with salt injection, is there a sensitivity to the duration and location of the injection? And could this sensitivity explain the observed mixing times at high concentrations?
So there is, there can be sensitivity to the mixing location, which I think we would expect for many systems. If we've got something that's highly turbulent, and so long as you're not injecting somewhere incredibly bad, say like right behind a baffle at the top of the vessel, the differences in mixing time are very small, and in fact we would often inject in multiple places as part of the sampling, and so it ends up giving an average time based on that. As we move to much more viscous systems, it becomes more and more a problem. And I think at that point, it falls within the challenge of then the design of the whole system about, well, where do we inject to actually optimize that mixing? It falls then within our challenge rather than a experimental mistake, I suppose. Was there a second half of that question, Claudio? Sorry, I forgot.
Second part was, could the sensitivity explain the observed mixing times at high concentrations?
No. So the higher concentration in this case is built up from the multiple injections. That's what moves us up the system. The actually volume that we inject each time remains the same. It's just a slightly more concentrated amount of salt solution that we add.
Just some more, couple of questions. So how many times does the conditioner in the stirred vessel go around the loop through the Silverson? Is the end point of the process defined by the product viscosity?
Yeah, so the endpoint is normally defined by a product viscosity. So that would be something that we're aiming to reproduce. So in the lab, it might be your product needs to fall within this range, and that would tell us when we actually get there. However, it does only tell us when the particular sample we've taken gets there, not necessarily the whole pot. The number of times through the mixer it depends on the quality of the mixing within the vessel. In fact, in the example that I've shown, the quality of the mixing within the main vessel was very, very poor for the thickness, and if I can move backwards, there we go. So you can actually see that we don't get a homogeneity really within the vessel, and you've still got some areas that are almost exactly the same conductivity as the base case, and it's being sort of sucked out the bottom. Where are we? Is it my right? The bottom right, as we look at it, corner. So in this case, it's actually passing through a very small number of times. In terms of this sort of graph here, we're passing it through a more controlled number of times. So this is actually done with one tank. We pass it through, collect it, and then transfer that second tank manually. So we actually have a control, and we, in this case, we were sort of doing up to 5-6 times. And as Mark actually commented, if you do it too many times, or your speed or shear rate is actually too high, you can actually destroy the conditioner. So we did have a number at very high rates where we passed it through, and we got sort of, instead of a lovely hair conditioner, we got kind of blobs and water coming out as we'd actually broken the microstructure.
So do we have time for one last question? Is still okay? So I have an interesting question. In the production plant, would this system need constant calibration for varying material species?
It would depend. It would depend on exactly what you wanted out of the system. So in the case of, say, generating a mixing time, so long as you've got a start point and an end point, that's actually sort of all you would need. So if you're looking for something to sort of go to a steady point at the end, that's all you need. You don't necessarily need an exact value, or there's less worry if the value drifts. So it doesn't need constant calibration. If you're looking for, say, calculating particular values from it, say a concentration, or directly mapping to the rheology, then ideally you would have to use some calibration. Just trying to think in practicality is how often it would be. It would depend on the systems, I think, but there would be some calibration needed in line with, I suppose, standard equipment calibration to do that. I mean, these systems have run, or this type of system have run on looking at collecting concentrations of materials, and they've run in process lines tested for sort of months without the need to sort of stop it and recalibrate the system separately.
Great. Thanks, Tom. I think that's all for the questions, right, Claudio?
Yeah.
Good. Thanks a lot, Tom. Very interesting. Always lovely to listen to, these techniques. Okay, next up, we've got Professor Jos Derksen. He's going to talk to us about simulations of viscous thixotropic liquids and how they respond to agitation. Jos, you're muted. Need to turn your microphone on. And if you can put your video on, that would be good also.
So now I'm unmuted, hopefully.
Yeah, we can hear you now.
And
That's good.
now you would like to see me, which is not
If
a good
we
idea,
can.
but I'll try anyway.
It's always nicer to have. Well, that's great. Okay.
Oh,
Off you
right.
go. Thanks a lot.
Cool. So now, thank you. How do I get rid of the bottom bar? Anyway, yeah, ready to go. So thanks for joining this webinar. My name is Jos Derksen. I'm in Aberdeen in the United Kingdom, which is, Aberdeen is the northeast of Scotland. And I'm going to talk about simulations and not about experiments. I deeply respect experimentalists and experimental results. But well, there's only 24 hours in a day and I would like to focus on simulations. I'm also not going to talk about hair conditioner. I'm going to talk about different applications that relate to industries that have sponsored this research. So this is oil sands mining, and this is clay suspensions, and also the paper industry, which I'm showing here, wood pulp for paper, fibrous materials. Now, thixotropy I consider time-dependent rheology. And in terms of modeling, I'm using a simple viscous thixotropic model that is based on networks or structuring of fluid. And that the cartoon here tries to explain that model. So we have an unstructured material here that if we let it, if we keep it at rest, in time it evolves into a structured material. If we shear that structured material, it breaks down again into an unstructured material. And the metric for structure and unstructure we call lambda, Greek letter lambda. So lambda is 1 for a fully structured material, lambda is 0 for a fully unstructured material. And in the thixotropic model, we connect lambda to the apparent viscosity. So if lambda is 0, we have an infinite shear viscosity, mu infinite. And if lambda is equal to 1, we have a higher viscosity, mu infinite, multiplied by 1 plus alpha. And well, what does the model need to contain? It needs to contain that lambda decreases under shear. It increases in time if there is no shear, and it goes with the flow, obviously. So we can think of a transport equation for lambda. So the left-hand side is simply the material derivative with u being the flow velocity. And then on the right-hand side, we have that breakdown under shear. Lambda decreases if we have shear and we have a proportionality constant k there, and lambda increases with time, and we have a time constant tau. So what we're dealing with here is a 4-parameter model. We have an infinite shear viscosity, we have a viscosity ratio alpha, we have a time constant, and we have a bit of a mysterious constant that we call k, which relates to the breakdown of lambda as a result of shear. Shear is a general term. It's not pure shear. It is in 3 dimensions deformation rate. All right, so we have a 4-parameter model. We need to connect it to some dimensionless numbers. We are at least, yeah, we are chemical engineers mostly. So we do some dimensional analysis. We consider a flow with some length scale that we call capital D, and a velocity scale that we call capital U, and a time scale that we have as D over U. We can define a Reynolds number based on the infinite shear viscosity, a Deborah number, which is a time scale ratio, so the liquid time scale tau divided by the flow time scale d divided by u. We have a viscosity ratio, zero shear viscosity over infinite shear viscosity, and we have this K that is shown in the equation below, which is dimensionless as well. And I'm going to talk a little bit more about that K, because that's a bit harder to interpret physically. If we think a bit more about our thixotropic model, and we take the limit when the Deborah number goes to 0, then this thixotropic model actually boils down into a shear thinning liquid. Breaks down, no, not breaks down, it evolves into a shear thinning liquid. So this equation for the apparent viscosity is shown in this diagram here. Viscosity divided by infinite shear viscosity as a function of shear rate is a decreasing function with increasing shear rate, hence shear thinning. And now we can define a characteristic shear rate, gamma dot C, and then gamma dot C is the typical shear rate where the viscosity has dropped to 50% of its zero shear viscosity. And that K of our thixotropy model, that relates to that gamma dot C. And we are able to have a new dimensionless number that we call capital S, which is the characteristic shear rate multiplied by the flow time scale. So here is our model. Here are the dimensionless numbers. And now we need to put that into some numerical scheme, some numerical method. And it's actually fairly straightforward. What we do is we couple a solver for this essentially scalar transport equation to a solver for the fluid flow dynamics. And for this, you can, in principle, use any flow solver and any scalar transport solver. I'm using for this a finite volume solver for the lambda. Remember, lambda is the structure parameter. Lambda is 1 fully structured, lambda is 0 unstructured. And maybe from a numerical point of view, the tricky thing about this transport equation is that it doesn't have a diffusion constant. And of course, there's always numerical diffusion, so we need specific discretization, TVD discretization, to suppress numerical diffusion. And then the coupling between the scalar transport equation and the flow equations is the viscosity being dependent on lambda. So that's the coupling from finite volume to Lattice-Boltzmann for flow solver, and then the back coupling from flow solver to lambda equation goes via the shear rate and via the velocity field. All right. Well, very quickly, I'm not going to talk about experimental validation, but I'm going to talk about verification. And what we do to verify this system is we looked at a very simple flow, the flow between two flat parallel plates driven by a pressure gradient or a body force. And we look at the time-dependent transition from a Newtonian flow to a via thixotropic flow to the shear thinning flow that I was talking about before. So on the left here, we see lambda as a function of the location Z between the plates, top plate, bottom plate. And on the right, we see the velocity in the x direction. And we start with a parabolic velocity profile, Newtonian parabolic velocity profile. And we, at some moment, we switch on the thixotropy and we see the transition from a parabolic profile to a shear thinning profile, the red curve. And at the same time, we see lambda here starting at no structure at all. Lambda is 0, evolving to a peaked profile for infinite time. And you understand the peak because in the center of the channel there is no deformation, a network forms, and lambda there is equal to 1. And here we compare semi-analytical solutions, the lines with numerical results, showing some confidence in our numerical method. All right, enough equations, I guess. Let's move on to mixing tanks. So what I'm going to focus on here is I'm going to talk about mobilization. So the typical situation that I'm interested in is a mixing tank filled with thixotropic liquid that has been standing still for a long time. So everywhere in the mixing tank, there is a structured fluid. Lambda is 1 in the mixing tank. And what I'm interested in is, okay, I switch on the impeller. How does the system evolve? How does mixing occur? How does the agitation mobilizes the liquid? I'm sure you remember we had 4-dimensionless numbers. I'm going to fix 3 of them. So I'm going to set a Reynolds number equal to 6,000, which, and I need to wave my hands a bit here, but which allows me to do direct simulations. That is, I don't need a turbulence model or a subgrid scale model as you would do in large eddy simulations. I also fix the viscosity ratio to 100, and I'm going to fix the fourth parameter S, which is the characteristic shear rate divided by the impeller speed N. I'm going to fix it to 1, and I'm going to look at the effect of the Deborah number. So the Deborah number 1 means a quickly responding liquid, and the Deborah number is 100, is a slow liquid. All right, so we're dealing here with a Rushton turbine, and I'm quite sure that there are many people in the audience that will now think, well, why would you use a Rushton turbine for a viscous liquid? And that would be an excellent question to ask. And then we're looking at a Rushton turbine baffled tank, and we're looking at a vertical plane in between the baffles. So what we see here on the left-hand side is a Deborah number of 1. We're going to see 40 impeller revolutions, and the colors are the structure parameter. So again, we start with this fully structured liquid. Lambda is 1 everywhere. And then we switch on the impeller, and then at a Deborah number is 1, you see something like this happening. You see that the colors turn from red into orange and yellow and purple in the impeller swept region and the impeller outstream. And we see that the impeller has some but limited success in mobilizing the thixotropic liquid at a Deborah number of 1. Now we're going to compare this with a Deborah number of 100. And for this is a very slow liquid. We need to do many more impeller revolutions in order to see some appreciable mobilization. So again, we switched on the impeller in a fully structured liquid, lambda equal to 1. And we look at the very slow development of the flow system. We are not able at these time scales to fully unstructure the liquid. I mean, on the left-hand side here, we see many, at least a significant purple region. Here we are not able to really break down the structure at the Deborah number of 100. I'm going to let this finish. And we're going to move to a Deborah number of 10. So in between the first one I showed and the second one I showed. And here are some interesting things, well, at least I think, interesting things happening. So we start seeing some unstable behavior here. So we see some sort of periodic, but not completely periodic oscillations. You see almost a full mobilization underneath the impeller, whereas the mobilization at the upper part of the mixing tank is very intermittent and seemingly very unpredictable. So here we summarize sort of these results. So what I'm showing here is time in terms of impeller revolutions, and the volume averaged structure parameter lambda, average lambda. You see that in all situations, so we have this Deborah number 1, 10, and 100. In all situations, the steady state is a lambda in the range of the average lambda in the range of 0.4, 0.3, 0.4-ish. But you see, well, a very different distribution of this level of structure inside the tank for the different Deborah numbers. Just quickly, let's see if we put in a different impeller. So we now put in a pitch blade impeller, baffle tank, vertical cross-section through the tank, starting again with lambda is 1, Reynolds 6000, S1, alpha plus 1 is 100, and we get something like this. And again, Deborah number is 10, gives some interesting instabilities. So while you're looking at this, you might also want to look at the right-hand side, which is a time series of lambda in the lower right corner of the animation that you see. And then you see here this quasi-periodic onset of an instability there. Maybe I was talking too much, so maybe I should let it just run and you interpret for yourself. So here the instability sets on. In the lower right corner, you see the quasi-periodic fluctuations in the structure parameter lambda. All right, so what I showed before is the structure parameter. Now let's look at mixing in itself, right? So now we have added a passive scalar to the system. So we have this active scalar lambda, but we also have a passive scalar. And what we're doing here is we're going to compare a Newtonian fluid, mixing of a Newtonian fluid in a at Reynolds number 6000 in a pitch blade mixing tank, vertical cross section, where within 60 impeller revolutions we are at the end of this animation. We have mixed the system quite well. Obviously, the top of the tank is the last to become mixed. But if everything is green and yellow, we are in a mixed situation. The system for a thixotropic fluid is different. It's not a really fair comparison because I compare Reynolds as 6000 for the Newtonian fluid with Reynolds based on the infinite shear viscosity of 6000 for the thixotropic fluid. So most of the viscosity in the animation that you see here is actually higher than U infinite. But you see that there is an issue with getting the upper parts mixed and getting the region close to the shaft mixed. All right, I hope if time permits, I would like to talk a little bit, to shift gears a little bit, because I'm pretty excited about this recent development. So we talked about fiber suspensions, and in my opinion, it is a very interesting opportunity to actually understand this structure formation in liquids by doing particle resolved direct simulations of rigid fibers and flexible fibers. So this is something I've been doing recently. We create fiber suspensions by fully resolving the flow, well, highly resolving the flow inside the fiber suspension. We let the fibers settle on the bottom of a tank, and we by putting a disc here, we start agitating the system, and we look at the mixing at a more detailed level. The spinning disc is not a very good agitator in this respect, so we need a better impeller to actually agitate this. These are examples. The ultimate goal of this sort of simulations, this sort of research, is to come up with a constitutive model about structure formation in fiber suspensions, and then again as to connect that structure formation to apparent viscosity or, well, rheological behavior. What I showed before were rigid fibers. We also do this stuff for flexible fibers. This is like al dente spaghetti, short al dente spaghetti in a mixing tank. All right, so this is coming to a summary or conclusions, maybe. So I showed you how to incorporate a simple thixotropy model, time-dependent rheological model, into a flow solver. Problems in general with rheology is that there is a multi-dimensional parameter space. When we focus on the Deborah number, the least thing I think I showed was that thixotropic liquids move in mysterious ways, where we see this unexpected quasi-periodic behavior. And I think an interesting avenue for better understanding thixotropy, specifically fiber suspension, is to perform direct simulations of such systems. That's what I would want to share with you. I'm going to stop share the screen, and I'll be happy to connect with you in terms of questions.
Thank you very much. Very interesting presentation. So while people are writing their questions online, I have a couple, if that's okay. I was just wondering about your thixotropy model, and I can only imagine what type of numerical issues you may get trying to resolve that equation. Do you need any special numerical scheme to keep lambda bounded between 0 and 1? Can it happen that it just starts jumping to values that make no physical sense?
Yeah, yeah. So you definitely you need to keep it bounded between 0 and 1, which there are. Well, let's say in K epsilon models, you need similar bounding strategy. So that's what we apply here as well. The most, what I think I already mentioned, that the most critical issue is numerical diffusion, because that transport equation in lambda does not have a physical diffusion, right? So, and then TVD schemes, total variation diminishing schemes are a sort of an efficient way, not a perfect way to limit numerical diffusion.
So what about the numerical issues when your viscosity tends to very high values? I have been having some issues trying to simulate yield stress fluids. So when the viscosity goes to very high values, we have to decrease the time step to incredibly low values so that the simulations give realistic results. Do you see that as well in your simulations?
Not really. So I don't dare doing yield stress fluids. That's a very different ballpark, at least in my opinion. See, I use this obscure lattice-Boltzmann method, right? So, and the good thing about this lattice-Boltzmann method is that it requires very small time steps. So I mean, that's a good thing and a bad thing. But I hardly ever get unstable because my time step is too large, as an example. So I can use the same time step I use, and that works. I use the same time step for solving my lambda transport equation and my fluid dynamics.
So we have one question from Alain. So it says, impressive work. Have you analyzed the macro instabilities observed at a Deborah number of 10? What physical mechanisms could be responsible for this?
Yeah, that's a very good question that I don't know the answer to. So I even haven't done, I should do it. I mean, it's a very good idea to do spectral analysis on these fluctuations and to figure out how they set on and how the spectral behavior depends on the liquid rheology. That would be an interesting thing to work on, actually.
I have a question also, Jos. On the last slides where you're simulating the suspension of the fibers, what insights do you have on the mechanism of suspension in these systems? We know, I think, suspension, solid suspension, the mechanisms of solid suspension in turbulent flows are, quite well mastered now, but probably not in these flows.
Yeah, so so I'm going to give a bit of a difficult answer to the question. See, I'm interested in getting the rheology of a fiber suspension out of the simulations, right?
Okay.
Our particle resolved simulations, blah blah. And for that, the mixing tank is a very bad thing. But I do the mixing tank simulations mainly for you guys, right? Because you want to see agitation. No, that's not. I mean, you write papers, etc. So, but so these simulations, as you may have noticed, I mean, if my fibers would have a diameter of 1 millimeter, the size of the mixing tank is a few centimeters, right? So these are very, very small mixing tanks, and I'll be happy to derive suspension and just suspension behavior from these simulations, but I'm not sure if that would be very interesting from a practical perspective, because these are almost microscopic mixing tanks. But there are very interesting mechanisms, right? So you put down that layer of fibers, of cylinders, and then you agitate it, and then you see that it's very hard to break the structure that has formed as a result of settling. So some fibers will never move. Because they are in a corner, or they are in some ordered structure on the bottom of the tank. But from a practical, I'm not sure how relevant that is from a practical perspective.
There's another question in this chat.
So has rheology been considered based on the population balance?
Can you repeat that?
Yes,
to
sorry.
start.
Has rheology been considered based on the population balance?
No, no, unless I don't understand the question. I don't use a population balance.
Maybe person who asked the question can maybe in the chat expand a little bit more, and then you can
Sure.
Yeah, that's a good option. Okay, well, let's move on.
Yes.
So we now have Dave Dickey, who's going to talk to us on industrial processes and equipment to handle fluids with complicated rheology. Over to you, Dave.
Thank you. I was asked to talk about scale up, and I had the initial reaction of the scale up problems that I would expect to deal with fall somewhere in the range between extremely difficult to nearly impossible. And so I've taken a little bit of liberty and taken kind of an engineering approach. You've heard a lot about the scientific approaches. This particular presentation is going to have no computer models, no sophisticated experimental equipment, and no list of graduate students. So we'll just start with that as kind of the starting point. And what it turns out to be is I picked some examples from some of the common industries where some of this complicated rheology develops. And they kind of fall into polymers, foods, and personal care products, of which we've already heard a few examples of those. And the equipment that gets used can be pretty ugly at times. It's often unique to the application of the industry. It's rarely researched or modeled, and it's frequently less than ideal for all the aspects of complicated problems. We've already had a little bit of that from the standpoint that many of these processes have a developing rheology during a batch, and so there isn't any one process involved. The other part of this is most of these processes don't involve chemical reactions. They're typically processes that are just formulations, multiple ingredients, different physical processes and properties, and some kind of changing rheology or other physical properties that occur during the process. Often the products are defined by their unique physical or formulation properties. Yeah, sometimes they've got some kind of viscosity associated with them, but the real objective is to get certain properties out of the process. The rheology is almost always some kind of a function of viscosity value, but it's not usually the real reason that you're making the product. Some of the places where we get into things that are defined by some of the rheology, quite often the use of polymers or thickeners. I'm going to give an example of a very high viscosity application involving some heavy duty equipment. We'll talk about the creation of some of the multi-phase products, things like the consumer products type things, where you get into liquid dispersion, solid liquid dispersions, and in some cases emulsion formation. It's the kind of thing that these are not in general uniform liquids or uniform fluids, even for that matter. And the function is often defined by some aspect of non-Newtonian rheology, and even that can be fairly complicated to model or even describe. So some examples then, the polymer products, I'm going to take a look at one as a filled polymer. There are certainly other processes and products that involve blending of different polymers. Food products, things like sauces, bread doughs, candies. One of the neat features of food products is everybody's kind of got an idea of what they are. The ingredients are non-toxic. The products are usually low value. The difficulty is that the value achieved as a result of processing is not greatly increased. And then the personal care products, toothpaste, creams, lotions, and I've got an example of that, which is much more general than what we've already discussed, but still something that's got some emphasis on how you go about doing the evaluation. The first is a high viscosity polymer process. They start with a high viscosity polymer. They add a fine powder to it, which gives you a filled type of product. The ingredients are placed into a heavy duty planetary mixer. The lid is closed on it and a vacuum applied. This is mainly a matter of trying to reduce the amount of air that's being dragged in by the powder and to limit the bubble formation. The products are mixed, or the ingredients are mixed together basically until you get a well-distributed polymer result. And then subsequent processing was done to form desired shapes and desired products, which I think this happened to be what you'd classify as a medical device. This is a picture of the polymer. It was heated before the process was begun, and it certainly heated up a bit more during the processing due to the amount of power that was applied to it, but it never really became something that you would consider a flowable fluid. And this is the powder, the filler, basically a ceramic mineral type material, about the consistency of flour. This is the mixer. This is a planetary mixer. Each of these devices rotates on its own axis, and then the axis of the two mixers are rotating around the center of the mixed vessel. And this is a picture of the product. I'm not sure how this applies to some of the things, but it is certainly not uncommon in terms of some of the things that are produced. Just recently been working on a process where they were working with a lower viscosity material, but going to about a 60 or 70% filler, which kind of messes with the rheology and the processing capabilities. A little bit about industrial and commercial food preparation is some examples of some of the unusual materials. Industrial food preparation is typical of the large-scale processes, things for bottled products, frozen foods, other types of food service items, that type of thing. Commercial food preparation is typically much more restaurant quantities and things of that sort. And the rheology gets fairly complicated here. It's a lot beyond viscosity because you're looking for taste and color. So there's some uniformity characteristics. You have pH and Brix, which is going to tell you something about how resistant this is to degradation or how much shelf life you get out of it. Mouthfeel is obviously a viscosity property, but I'm not quite sure how you define it. A lot of these things have some solids content to it. Coating characteristics are quite common in terms of what you're trying to do with it. And the equipment that's used for this is kind of multi-function stirred tanks. The one on the left has an offset turbine mixer along with an adjustable baffle. This type of equipment or this type of a mixing operation is done for low to medium viscosity materials. The vessel on the right is designed for more viscous materials as well as materials that may cover a very wide range of conditions during the processing. And again, it has an offset turbine mixer, but it has a sweep type impeller. And this one, I think, even has scrapers on it. And it still has a baffle in it so that there is some additional control over what might be going on at a lower viscosity condition. A good example of this might be a sauce, barbecue sauce or something like that. Starts with a water base. They add sugar, vinegar, oil, vegetable puree, say a tomato paste or something like that. May add some thickeners, certainly can add some spices and that type of thing. And then you have a functional viscosity measurement. And this is with a Bostwick consistiometer. And what this is there is a little chamber at the left side of this where this gate is pushed down. It's a spring-loaded gate. The material is kept in this little chamber. The temperature is measured or allowed to equilibrate very often to atmospheric pressure. And then the little gate is popped open and the flow is allowed to proceed for 30 seconds or something like that. And the final measurement of the property or quality or whatever is determined by how far the material flows in 30 seconds or whatever. And so quality standards are based on, 15 to 10 seconds or 10 centimeters, something of that sort. Again, purely functional. I don't know that there's ever been any real attempts to try to get those to match up with specific viscosity measurements. An example of commercial food mixers is kind of interesting. Hobart might be a name that most people might recognize, began making electric motors back in 1897. Hobart Manufacturing Company started making commercial food mixers in 1914, and they're still making pretty doggone nearly the same thing today in Troy, Ohio in the US. And I found this to be particularly interesting. Out of the first edition of Perry's Chemical Engineering Handbook, there was an entire chapter on mixing. And these are examples of some of the mixers at that time. And the one on the left is a good example of a planetary commercial food mixer. And the one on the right, we'll see a little bit later on in the context of some of the mixing equipment that's used for personal care products and that type of thing. Here we see one of the current commercial food mixers. It's come in a variety of sizes, planetary mixers. The device on the right is a dough hook, which is about as crude an impeller as you can get, but they're used for some common problems such as baking a bread dough. And this just simply shows how it looks when you start out with flour and water. It probably had something in the way of shortening and leavening ordinarily, but this was a matter of we were just simply looking at how the dough hook was going to mix the material and what ended up happening. After about a minute or so, the material starts looking a little more dough-like, and you've obviously made some rather drastic changes in both the viscosity and the elasticity of the material, because you're developing a gluten here from the flour with the water. And a little bit further on, after a couple minutes, you're basically dealing with a ball of dough. And at this point, what you're trying to do is you're trying to knead it and develop the gluten so that you can actually trap gas bubbles that are released as a result of the leavening and the bread dough. What happens when you go to industrial scale? Pretty much the same thing. This is just an example of an industrial bread mixer. It's tipped up or it's tipped open. This is how it would be used to dump the material out, but you can see the type of blades or the type of mixing equipment that's actually used to create the bread dough. I did throw this one in just kind of to give a feel for, this is more of an intermediate to low viscosity application, commonly called a Dickey mixer. It has a series of paddle wheels that rotate in the bottom or near the bottom of the vessel. And this is designed to disperse liquids for making things like salad dressing. So you're probably dispersing an oil into an aqueous material. And then some examples of personal care products. And we've had a couple of comments about these and got into a little more detail of the formulation. But what you ended up with is, in this particular case, is a very simplified form of one of the processes that we had to look at. I broke it down into 3 steps, which actually is the way we broke down the process itself, because each of the steps involved different viscosities and some differences in the processing conditions. And I think we even changed the rotational speed of the mixer at points in the process. The first one was just mixing water and some kind of copolymer for about 10 minutes at ambient temperatures. The second step involved the addition of surfactants and some other ingredients and mix for an additional 30 minutes to get to uniformity. And the final step was a little bit of what was addressed earlier about adding sodium chloride, which then was heated to 35 degrees C to make sure that you got the salt dissolved and distributed in an additional 20 minutes of mixing. The actual process involved the additions of more than 20 different ingredients, which included colorants, fragrances, a variety of other materials, things like perhaps a sunscreen or something of that sort. What you get out of that is, and again, much of this is a matter of, okay, here's the thing we want to produce. Here's the equipment we have available to produce it. And what you hope for is you either have some very robust equipment or some stuff that will absolutely do pretty nearly anything. And some examples of this are, this on the left is a double mixer that has a high-speed shaft with a couple of sawtooth blades on it. It has a sweep impeller in it that provides some turnover and some mixing of higher viscosity material. This is the type of thing that might be used in creating a some kind of a dispersion and a end product that's an emulsion. The one on the right is just a similar type mixer, except the type that might be inserted into a can for mixing and pulled vertically out of the can. Some other examples, these are some triple function mixers. The one on the left has the sawtooth blade on a high-speed shaft, has a turbine mixer at a slight angle on the right, and again has a sweep impeller. The one on the right is a little more unique in the sense that I actually encountered one of these, and it had a vertical shaft with a couple of high-speed sawtooth blades for dispersion. It had a sweep anchor type impeller. And on the left, it had an auger. And the auger was in there to provide the vertical mixing that you don't get very well with sweep impellers and radial flow mixers. And quite honestly, that's about the only one that I have seen another one, but they're relatively uncommon and show up in some unusual applications where you find augers. Not probably the best. And then back a little bit to the one that was shown in the Chemical Engineer's Handbook from 1934. This has a sweep impeller with a scrapers on it and some blades that are inside of the anchor part of it with a counter rotating turbine blade in the center, which lots of different things that can be done. Have seen these used in, again, some of the personal care products, as well as some other kinds of medium to fairly viscous materials. And the last one I put in here, kind of interesting to have seen one in an earlier presentation of what I consider to be container mixers. And these are mixers that have no internals. They just simply rotate or wiggle the container well enough to cause the mixing to take place. And the reason I put this in here is actually I encountered a particular process that had been development work done in one of these types of mixers. And I honestly couldn't figure out how to do it with an impeller in it because the product stuck to the impeller better than anything else that was in the process. But here's the case of the centrifugal mixer with a rotating container that gets you the circulation pattern that over not terribly long period of time will blend some fairly viscous materials with absolutely no internal blades or internal mixing device. And this just simply shows a case of where they take some viscous materials in different colors, and then look at how the material is blended and how it mixes. This type of equipment is extremely effective for laboratory mixing, a little more difficult to duplicate in commercial sized processes, although there is some mixing equipment that gets up into a size where that you can work at larger scales. And in most cases, some degree of just experimentation and empirical adjustment is necessary to make them work the way they're supposed to. And the last one is a resonant acoustic type mixing, and demonstrates that it's capable of mixing some. Again, this is just up here at the top is just simply a laboratory container that's held in place, but it shows that what you have is corn syrup, powdered sugar, and sand, of which all three are probably some of the most dissimilar materials. And yet in a 30-second mixing time, admittedly a small container, but it is the kind of thing that they were successful in getting the material to not only turn over, but actually mix together rather well. And I think the particular people that I've seen use this are delighted with the fact that it's relatively easy to clean or throw out the beaker when you're done mixing the stuff, almost regardless of how difficult it is. And then this just shows here in a minute a little different angle to get a sense of how the material is being moved as a result of the acoustic vibration. So anyway, out of that, I guess the conclusion that I tend to draw out of this is the fact that lots of different types of both conventional and unconventional mixing equipment gets used for some of these high viscosity industrial mixing application. There's a wide diversity of products. I've often joked that it's kind of like I didn't know some of these products existed or that you'd even be able to sell some of this stuff. And then the viscosity is often a result of either multi-phase or polymer thickening fluids, and is definitely being driven into the non-Newtonian area for the product characteristics. And that's basically what I wanted to present. The problems are very difficult to resolve into you start with this and get to that. Much more of it is you start with existing equipment and you start with an existing process and figure out how to put the two together. Open for questions. I didn't notice whether there were any or not.
Thank you, Dave. Very good overview of very challenging processes. So while people are writing their questions on online, please use the Q&A tab. I have a couple of questions. So from your experience, what is the rheological feature of the fluids that you have been working with that causes the most challenges for mixing? Is it viscoelasticity? Is it yield stress? Or
yield stress is a very interesting one. Although I think one of the problems is that a lot of people don't even recognize that dissimilar viscosity is a problem. My favorites are food problems. If you want an interesting viscosity problem, try mixing corn syrup into water. They're mutually miscible in any combination and are really nightmarish. But the one that's really fun, try putting ketchup into water and stirring it with a mixer. And it's even more fun because it goes through all the stringiness and all the crazy characteristics in the process. I mean, and those kinds of problems are a little bit unrealistic in the fact that you're probably not going to encounter them exactly. But I had a pharmaceutical company come to me and said, we're trying to mix a viscous liquid into a low viscosity liquid. And we figured it would go together very easily because they were mutually miscible. And we couldn't figure out why it took so long. I mean, it's the kind of thing that some of this stuff is simple stuff that if you've done any amount of work in the area, you probably can anticipate. But most of the rest of the world, forgets about or has no clue as to the nature of the situation.
So there's a question online, so I'll give priority to that. So Marcio Nellis says that this was a very nice lecture. So he said, could he repeat the last example of stuff difficult to mix? I'm not quite sure what that was.
The last example was just simply a combination of a viscous liquid, which was corn syrup mixed with powdered sugar, which is a very, very fine powder, and sand. Now, what the utility of this is escapes me. It is the kind of thing that it is a good example of some of the complexities that you might get into.
Alain has another question. So it says that you did not mention the energy consumption of each mixer. Is this the secondary issue?
Usually it's unknown until you try it. I mean, part of the problem with this is if you just simply take a look at the mixers that are involved, it is extremely difficult to figure out how counter-rotating equipment or multifunction mixers are going to behave. And in general, most of the mixers that are used like this, the motor on them is probably 5 times the size that is needed for the original application. And the assumption is sooner or later, somebody is going to mess around and get the viscosity high enough to load whatever you put on it. So it's a situation, the industrial practice is not very good. And actually, I'll toss it out to this group. One of the most interesting power numbers that I'd like to know is a rotating disc, because you have a whole bunch of sawtooth impellers. The rotating disc must be about the lower limit of the power number, and the upper limit can be huge because the blades can be pretty nearly anything. And all of them are pretty much unknown.
But also about the geometries, you show some pretty crazy geometries that have been around since the 30s. I think that was the earliest example that you have shown. Is this kind of a natural selection of geometries that we have, and the ones that prove to be the most robust are the ones that are used, or it's just inertia from an industrial point of view?
Let me put it in my own perspective. I'm a consultant, and most of these people are having problems because this equipment or the process is not a common equipment. It's not a simple stirred tank. It's not a uniform liquid. It's not a known viscosity. It's something weird to begin with. And as a result, you have a tendency to see an awful lot of the odd equipment in it. These are all examples of things that I've seen not just once or twice, but in many cases, multiple times. It's the sort of thing I avoided some of the really oddball equipment I've seen. It's the kind of thing that it's out there.
Great. I don't see no more questions online.
I must have scared everybody.
No, you're great. Great, Dave.
Very interesting.
Okay, well, it is now almost 5:15 Central European time. So, Dave, thanks for that really practical talk. Exactly what we were looking for, because we wanted to go from more academic style presentations into very practical ones and applied. So it made the 4 of you. I'd like to thank the 4 of you for taking the time to prepare these presentations that were really interesting and to have made this afternoon very successful. I'd also like to thank Martin, who has been in the background the whole time and has been in the background, well, not necessarily in the background, in the forefront for the last couple of months, organizing all of this. So she looks after all the promotion of the events and the technical aspects, and all of the rest. So with that, I think I'd just like to conclude and say thank you to everyone for having joined us this afternoon. And
Thank you for the opportunity to present it. I hope people got something out of it.
Yeah, I'm sure they did.
Definitely, yeah.
Great. Okay. We'll see everybody soon, somewhere around the globe.